All right. So we are going to try problem 20.9, in which use the following set of pressure volume data to find the best possible coefficients A1 and A2 for the equation of state shown below. R has a known value, temperature is 303 Kelvin, and so what you can think of is PV divided by RT, which is a constant. R is known, T is known, equal to 1 plus A1 over V plus A2 over V squared. This fit function is given to you, and the data is presented in terms of pressure in atmosphere and volume in milliliters. Before you start, what will be the value or the units for A1 and A2? What is the unit of 1? What? Sorry? Unitless. It's a pure number. PV over RT obviously also has no units, because you know PV equal to nRT, the ideal gas equation, where N is number of moles. So A1 over V should be unitless, which means what is the unit of A1? It should be same as volume, right? Yeah. So A1's unit should be milliliters, and A2's unit should be milliliters squared. This you should know from the outside. Now, how will you now identify your Y value and X value? What is your Y and what is your X?
Do we assume that pressures are X since it's first one?
See, if you plot this data as it is, pressure and volume, you won't get any physical trend out of it. The problem itself gives you that this is the equation of state to use, so you can write or you can plot PV over RT as a function of 1 over V. If you do that, you get a quadratic curve which goes something like this. That is this curve, PV over RT equal to a function of V, and that function happens to be 1 plus A1 V plus A2 V squared. So you want to construct your Y as PV over RT and your X as 1 over V. If you do that, then what is your fit function? Your fit function is Y equal to, you are already given 1 here, so you don't need a fit constant. You can just write 1 plus A1 times X plus A2 times X squared. Yes? Did you have a question?
I did. Why did we? How would, like, what intuition would we need to figure out that our X would be 1 over V?
It's already given in that fit function.
Okay.
If this weren't given, you have to be, this equation is called, forget the name of the guy that came up with it for the first time. You have to be that guy to think of it, theorize it, but in this problem at least it's given to us. So if you get up to here, your data is presented as P and V. You can put this in Excel. So remember, in your exam, you will have access to your computer and Excel. So let's do this problem as I would do it in an exam. All right, so I have my module 3 examples file, which I'm going to actually download and use. All right. So what do you do? This is what is the problem number here? Sorry, enable editing. 20.9. Thank you. Problem 20.9. So I have pressure in what units? Pascals?
This atmosphere.
Atmosphere, and volume in milliliters. And I have the data here, so I can just. Oops. I need this. All right. I have my pressure and volume, and I'm going to write PV over RT equal to 1 plus A1 divided by V plus A2 divided by V squared. I'm going to get, I'm going to keep X I'm going to define X as 1 over V and Y as PV over RT. So what is the value of R given to us? 82.05 milliliter atmosphere per gram mole. That looks hideous. 82.05 milliliters atmosphere per G mole.
Kelvin.
Sorry?
Yeah, gram mole Kelvin.
Gram mole Kelvin. Okay, thank you. See, I knew I would miss something. And temperature is 303 Kelvin. So I'll just multiply RT and I'll keep it ready as milliliter atmosphere per G mole. So I have to redefine my X, which is 1 over V, and my Y, which is PV over RT. Go ahead, get up to here. So 1 over volume, I can easily do that. Oops. 1 over volume. And then I have pressure multiplied by volume divided by RT, which I have to freeze, enter. So before you plot this quantity, you can just check what is the plot between pressure and volume directly. That comes out to something like this. Okay. And if I plot these two, I get something like this. That is, this is PV over RT plotted versus 1 over V. And this is pressure plotted versus volume. See, the problem specifically asks you to use this fitting function and figure out what A1 and A2 are. You are not asked to try any other fit. They want the values of A1 and A2, and often, usually these type of coefficients have some connection with the theory. So they first figure out this like the question you asked. They come to this functional form based on some physical principle, and then they use the data to work out what this constants must be. So right now, your goal is to finally report what is A1 and A2. Okay. So keep focused, be focused on that. So now you can right click here and say add trend line, and a linear trend looks good. I don't see a problem with that. But if you go for a polynomial fit, it's even better. So you have 4 data points. If you fit a quadratic curve, how many degrees of freedom are you left with? Quadratic curve involves how many fit constants?
I have none. I have- You're right.
3 fit constants.
Yeah.
You have 4 observations and 3 fit constants, which means only 1 degree of freedom. If you fit a linear, how many fit constants?
Yeah.
2. You're left with 2 degrees of freedom, which is actually marginally better. But in this problem, the theory dictates you need a second order curve, and this is what you will get as fit constant. Now you can do the other way also, which is try to have equations set up. What are those equations? Sigma y equal to a naught n plus a1 sigma x plus a2 sigma x squared. Sigma xy equal to a naught sigma x plus a1 sigma x squared plus a2 sigma x cubed. Sigma x squared y equal to a naught sigma x squared plus a1 sigma x cubed plus a2 sigma x power 4. That is 3 equations in 3 unknowns that you need to solve for. So let's start working this out. X squared, x cubed, x to the 4th, xy, x squared y. In your exam, if you get up to here and you can use, if you are able to use your MS Excel to correctly get the coefficients without going through these steps, I'm actually okay. Because most of the time, we try to design the questions such that the trick is here and not here. That makes sense? If you can use Excel to give you these coefficients directly, go for it. That's up to you. So if you substitute for sigma x, sigma y, and all these coefficients and you solve, you should get. See, here is the problem. Here's the problem right here. If you use a naught instead of 1, you are getting actually 3 variables that need to be solved. If you use only 1, that is, if you already specify the fit equation to have a 1, you can go here, and when you say fit, you set the intercept to be equal to 1. Set the intercept equal to 1, then directly you can get the fit equation with only 2 parameters. Okay, that is, I'm already setting the intercept equal to 1 by putting it in the software. So this is my second order coefficient and first order coefficient. Now question for you, how would you rewrite this if there are only two fit constants? Because this is written for three equations in three unknowns. I'm restarting here for your convenience. Your fit equation is y equal to 1 plus a1x plus a2 x squared. How will you set up two equations in two unknowns to solve for a1 and a2? Do a summation over y, or do a summation over everything. Sigma y equal to n plus a1 times sigma x plus a2 times sigma x squared. And then multiply by x, sigma xy equal to sigma x plus a1 multiplied by x squared plus a2 multiplied by x cubed. You need only two equations which you have for two unknowns. So now use these coefficients and see if you get the same value. Two equations, two unknowns. What do we have? What is sigma y? What is sigma y? I need to take this and what is sigma y? 3.95. So I have 3.95 equal to n equal to 4 plus a1 multiplied by what is sigma x? 2.07 times 10 to the minus 4. And then what is sigma x squared plus a2 times 1.12 times 10 power minus 8. And then what is my second equation? 2.05 times 10 to the minus 4 equal to 2.07 times 10 to the minus 4 plus a1 times 1.12 times 10 to the minus 8. Actually, I'm going to write it out on the whiteboard. Plus a2 times, what is a2? Sigma x cube, which is 6.23 times 10 power minus 13. So I have this functional form. How do you generate two equations? Sigma y equal to n plus a1 sigma x plus a2 sigma x squared. That is the first equation, which is 3.95 equals 4 plus a1 times what? Plus a2 times 1.12 times 10 power minus 8. If you have two equations in two unknowns, Gauss elimination is your best choice. It's very simple. So you can write a2 equal to minus 0.05 plus 2.07 times 10 power minus 4 times a1 divided by 1.12 times 10 power minus 8. And then how do you generate the second equation? Sigma xy equal to sigma x plus a1 times x squared plus a2 times x cubed, which is the second equation we wrote. 2.05 times 10 to the minus 4 equals 2.07 times 10 to the minus 4 plus a1 times 1.12 times 10 to the minus 8 plus A2 times 6.23 times 10 power minus 30. So you need to substitute for A1 and substitute for A2 in terms of A1 and solve. You can complete it from here and verify if A1 equal to and A2 equal to. Let me see what values I got. A1 should be equal to minus 231.67 and A2 should be equal to minus 104,896. 986. So it involves two steps. One, taking the original data and replotting it in terms of a new x, which is 1 over v, and a new y, which is pv over rp.
It's okay for your Y to have like both independent and dependent variables.
Sure, you have to identify a combination of the variables so that the two will have a definite relationship between them. That's okay. In fact, in one of the problems we did, we plotted y over x versus log x. Same situation. Any questions? So we try one more example. So I'm saving this. All right.
So you need sections that you're going to be trying to pull examples from.
I mean, chapter 17, we did linear regression, quadratic regression, and transformations. It might be just like a table given to you with fit x versus y, or it might be a word problem which comes from chapter 20. But the word problem will not be heavy. It will be like pretty straightforward, like what we did.
Thank you.
They have a lot of non-linear regression, which we didn't cover through pencil and paper. We did only MATLAB. So maybe that I won't ask. This problem we already did. So all right, so problem 20.33. Problem 20.33. Following model is used. It's frequently used in environmental engineering to parameterize the effect of temperature in degrees Celsius on biochemical reaction rates per day. K is equal to K20 multiplied by theta raised to the power t minus 20, use the transformation to linearize this equation, then employ linear regression to estimate k20 and theta, and predict the reaction rate at 17 degrees Celsius. That's the question. So, step 1, I want you to tell me what transformation shall we use to linearize this equation. I have to. So what transformation will you use to linearize the equation? Remember, theta is the parameter, t is the variable.
Would you want to use exponential?
Exponential, so let's see here. You want to take the exponent of both sides?
Actually, both sides.
So you have k equal to k20 theta raised to the power t minus 20. So whenever you have these type of power law relationships, don't do the exponential, do the logarithm. Natural logarithm of k equal to natural logarithm of k20 plus t minus 20 times the natural logarithm of theta. Okay, so we'll call this our y, we'll call this our b, we'll call this our x, and we'll call this our m. So y equal to b plus mx. You have to plot y equal to ln x or ln k versus x, which is the temperature shifted by 20 units, t minus 20. If you plot these two, you can expect a linear trend, and if so, you can get the intercept and slope and use them to get the values of k20 and theta. What is the next step? You are in the exam hall.
What? Yeah, the body.
So go to your Excel. Problem, what's the problem number? 33. Thank you. 20.33. I have the data which is here. Okay. I just decided that so temperature in degrees Celsius and K in per day. What is my X value? X equals T minus 20, which is T minus 20. And what is my Y value? Natural log of K. See, if taking the natural log makes you uncomfortable, you can do it as how will you get rid of the units for K? You can do natural log of K over K20 equal to T minus 20 multiplied by natural log of theta. So that your K will not have, or your Y will not have units. K divided by K20, and actually that would present a problem because I don't know my K20, right? So let's just go with ln K like we previously did. Ln K, what is natural log of K? All right. So now you plot these two quantities. plot these, add a trend line, linear, display the equation. Here's your equation. Here's your equation. Slope is what? 0.671. What is my slope? Slope is natural log of theta. Okay, so I'll write it here. So slope is, this is my slope. Oops. My slope equal to natural log of theta, which means theta should be exponent of the slope. What is exponent of 0.0671? Theta equal to exponent of 0.0671, which is 1.0694. And then I have my intercept. What is my intercept? It is equal to natural log of K20, which means K20 should be exponent of the intercept, which is K20 equal to exponent of minus 1.0448 or 0.3518. Then you are asked to evaluate what is the rate at 17 degrees Celsius. So rate K at 17 degrees Celsius is equal to, so what is your original equation for that? This equation, yes. K20 should be K20 multiplied by theta raised to the power temperature, which in this case is 17 minus 20. That's your rate at 17 degrees Celsius. I know I went through that pretty quickly. Take a minute, ask me if there is any question.
I was following pretty much until, where did the K sub 20 to the 0.3518, where did that?
So the intercept is this one, right? From our transformation, whatever is the intercept should be equal to the log of K20. So the K20 should be the exponent of the intercept. That's what I've written. Is if you take the exponent of this number, you will get it.
Would you want to, kind of what we call it, the standard deviation? I think we talked about that last time we were doing this.
Well, in a specific problem, it might be asked to get you the standard deviation of the fit, for which you need the SSE or the S squared. So how will you get that? Since you brought it up, that's a good question. You want to get the difference between fit minus Y value, or Y fit minus y data. So before you do that, you need to get what the fit value is. So how will you compute the fit value? Y fit, that is equal to k20 times theta raised to the power t minus 20. Okay, or in this case, this is k fit minus k data. Okay, so how do you write this? This is k20. What is k20? It's right here, plus f4 times theta, which is right here, plus f4 raised to the power t minus 20. So here is your fit value, which is 0.1374, pretty close to 0.14. 0.205, pretty close to 0.2. 307, 31, 46, 46, 688, 69. So that the fit is pretty good. So you will compute the difference between the fit minus the y, the real data. Okay. And then you will square this. You will square it and then you will sum it. Okay. This is your SR. The standard deviation SY bar X, this is equal to, formula wise, this is square root of SR divided by N minus M, or divided by degrees of freedom. So in this case, this is SR. What is the degrees of freedom? How many data points are there? 5 data points, 5 rows. How many fit constants? 2. Say it firmly and then confidently. 2. So how many degrees of freedom? 5 minus 2. So 5 minus 2, or I'll write it as number of observations is 5. Number of fit parameters is 2. So degrees of freedom is 5 minus 2, 3. So last step, the standard deviation would be square root of this SR divided by 3. 0.00393. Sorry?
Could you please click on my six so we can follow how you got that column?
I6. Okay. I6 is simply taking the difference and squaring it.
Then we have them all up for our SR value.
Sorry, come again?
Then we have them all up for our SR value.
Yep, add them all. SR is the summation of the squares. Yes.
Is your difference always the fit minus the data, or is it data
Well,
plus the fit?
our purpose is SR is the difference squared. We do the squaring to get rid of that sign. So you can do it both ways. In my mind, I always think as difference is between what it should be minus what it is. In that case, it should actually be the data minus fit.
What is, so, what is the number of iterations that would find this?
I'll expand it. Number of observations, which is basically number of data points. Yes.
So in the exam, you're not actually going to see our Excel sheet. So what do you actually want us to put on the paper?
So in the paper, I will be asking you specific questions. Like for example, he will ask you, what is say K17, or if we give you this the form, we'll ask you what are the values of K20 and theta. And then we'll ask these, like you will be given a table to fill out. Number of observations, blank. Number of fit parameters, blank. Degrees of freedom, blank. So only if you know how to compute this, you will get it back. So I won't ask you to upload any file, because the reason I don't do that is you have access to any source of information. So we can't verify where you are getting your Excel sheet from if anybody chooses to do anything other than being honest. So we are just asking you for the response. I bet those people at Check cannot get you a response fast enough. So this is trying to beat them. All right, good. I have to go at around 1:55. So let's try one more example. Example 20.53. The acceleration due to gravity at an altitude y above the surface of the earth is given by this. The data is given to you. Nothing is suggested whether it should be a linear fit or non-linear fit. You have to make your own judgment to compute what is G at 55,000 meters. Okay. So step 1, enter the data into Excel. Problem 20.53. Enter the data into Excel. I'm going to be a little rushed here. I apologize. Okay. Nothing is told to you. So let's try plotting it first to see what goes on.
Use your brain and know that gravity is an exponential thing.
Yeah, if you know it already, sure. That is what is called experience.
Yeah.
So if I just plot the data, I'm getting some data points which may or may not be a linear fit. So if I try linear, I'm getting almost a perfect fit. Okay. If I try something else, like for example, if I try anything else like a polynomial, I'll still be getting a good fit, but that may not be necessary. So if nothing is told to you, based on the given information, it seems like a good linear fit. You just need to plug in 55,000, which will appear somewhere here, and do this. On the other hand, it's also a good candidate for your interpolation. You can also do interpolation. 55,000 is between 30 and 60. You can use this linear fit as justification for using a linear stencil. Put 55, which is almost closer to 60. So probably the value will be closer to 9.68, and you can finish it. As far as regression is concerned, please practice as many as you can related to transformations. There will definitely be transformation involved from getting the data and answering the question that is being asked. Okay, and this is getting recorded, so hopefully others will also see. Are there any specific examples you want me to try or questions you have? All right, so I'm going to stop this here.